Hello, my name is Evan Cardenas, and this is my report for Lab 6, Magnetic Molasses. So the purpose of this lab is to study magnetic induction and eddy currents by seeing how a falling bar magnet interacts in an aluminum tube. To kind of just cut to the chase, the results were uh, for like the actual experiment, we got 1.43 seconds. And in the computational, we got 0.211 seconds, which is, a bit of a difference. So here are some of the fundamental physics principles. So the first is Newton's second law, which is just, F equals ma, force equals mass times acceleration. That's a basic one. The second is Newton's third law, which is just every reaction has an equal and opposite reaction, uh, for obvious reasons, right? It's gravitational force, and there's also magnetic force, and they kind of have an equal opposite thing. There's Faraday's law, which is when a magnetic flux or field change with time, it creates an electromotive force. And the Biot-Savart law, um, it's an equation that just says how a magnetic field produced by a constant electric current is created. So here's the initial model. That would be the picture. So the initial conditions are, of course, the magnet and the stopwatch, with the system being the magnet and the tube and surrounding being, well, of course, everything not in the system. So here is the observed model. So the mass of the magnet was 0.028 kilograms. It had 1.47 amperes by meter squared. The tube length was zero point 0.3 meters. The width was 0.007 meters. The inner radius was 0.02 meters. The outer radius was 0.032 meters. And the average time was 1.43. We did 3 trials. As you can see, they all just averaged to 1.43. So here is the first part of the code. We just kind of, this is just initializing everything. This is the second part of the code. It's just a while. It's just a while an if function inside of it. It's basic. It's basic Python. And here is what it ended up being. It ended up being kind of like just ended up being like a straight line, as you can see. With the magnet, of course, dropping down the tube. So here are some of the assumption times. So the assumption is that the magnet acts as a magnetic dipole to apply the Biot-Savart law. Just makes sense. The other assumption is there's no air resistance, and the only forces are magnetic and gravitational. Of course, as I said previously, the times were for the actual experiment was 1.43 seconds, but the computational was 0.211 seconds. Now, possible sources of error. There could, of course, be other forces on the fields, perhaps like another magnet or something of the like, or a piece of metal on the table that was just attracting it. There could have been friction from the magnet inside of the tube. Once you drop it down the tube, there's really not much you can do to stop it from hitting the walls. And finally, the stopwatch could have been stopped early or late, which is probably most likely the biggest source of error. Um, Discussion question 1. So, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So, if the tube behaved like a perfect conductor, the induced current would be extremely large, nearly lossless. These currents would generate a magnetic field that very effectively opposes the magnets of motion. As a result, the magnet would fall dramatically slower, uh, approaching a terminal velocity, actually. And in the ideal limit, the magnet could even kind of like levitate or descend so slowly as to almost be levitating because the electromagnetic dampening becomes nearly perfect. And so, what if holes or slots are cut into the tube? How would this affect the ring current in your model? So cutting holes or slots kind of breaks the path that the induced current relies on, and they would just be weakened severely and would reduce the opposing magnetic fields, which just means the magnet falls faster because the electromagnetic braking just kind of becomes less effective. And the more holes, the more it kind of breaks apart. But yeah, that's the video. Thank you, and have a good day.